Here's a 2D vector explosion kind of question. This is a past exam question. A stationary mass exploded into three pieces, A, B, and C. Piece A had a mass of 2m, piece B had a mass of 2m, and piece C had a mass of m. The multi-image diagram below shows the motion of the three pieces after the explosion. Only the first image for piece C is shown. Assume that the system is isolated and the time between each image is constant. Use the law of conservation of momentum and a vector diagram to determine the position of the next image for piece C after the explosion. Draw this image on the diagram above, and it's worth 4 marks. So this kind of question does require the use of a ruler. It does require some careful drawing. It doesn't require any maths. This is these multi-image representations. They're always just diagrammatic problems. There's a couple of different variants. So you can have this kind of situation where it's an explosion. The other situation's a collision. It's kind of mostly similar things, but there's a couple of different tricks that we use for the two different types of problem. So conservation of momentum is how we're going to find the new location of piece C after, one extra frame, if you like, one next image of piece C. If momentum is conserved, note that it says initially the mass is stationary. Initially, if the mass is stationary, that means the total initial momentum is 0. If momentum is conserved, and we are using the law of conservation of momentum, so we have to assume that the momentum is conserved. If momentum is conserved, then after the explosion, the total momentum of the three particles, three pieces, the total momentum must sum to 0, because that was the initial momentum of the system. So how can we show that the total momentum of A and B and C is equal to 0, and then use that to find the momentum of C? That's what we've got to do. So the first thing to realize is that for pieces A and B, they both have a mass of 2m. So I'm going to write that here just to remind myself. And they've got their directions of motion shown. These images are taken with a constant frame rate, so there's a constant time interval between each image. That means that the velocity of these particles is represented by the direction that they're moving is shown, and obviously if they're moving faster, they're further apart. If they're moving slower, they're closer together. We're interested in the momentum, not just the velocity. So the way that we multiply the velocity by the 2 to turn it into a momentum is we're going to draw a momentum vector that spans 2 gaps, 2 time intervals. So the momentum of particle A, excuse me while I rotate the page so I can see what I'm doing. The momentum of particle A is this vector. It's up, and it spans those 2 gaps. Yeah. The momentum of particle B is down and to the left, and it spans those 2 gaps. Should be able to connect going down this way. And again, labeling things to be super clear. This is PA, a little vector hat, and this is P sub B, a little vector hat. What we've got to do to find the momentum of C and therefore the location of the next piece. Firstly, note that C has a mass of 1m. So we're just after the single next image. We don't have to draw 2 images or whatever. Just one next image. If momentum is conserved, the total momentum is going to be 0. How that's going to look on a vector diagram is that PA plus PB plus the PC that we haven't drawn yet are going to be the 3 sides of a closed loop. So if we follow the vectors around from tail to head, tail to head, tail to head, the third vector is going to close the loop and start off back where we started. That means that the total momentum is 0. So let's construct a triangle and see how that goes. So I'm just going to add PB to PA first, right? What I'm saying, I guess, is that, maybe I'll scribble down here, P total equals 0 secnewtons, which is equal to PA plus PB plus PC. Oh, got their little vector hats. So let me construct this triangle of PA plus PB plus PC. So here's PA. I'm going to draw a PB on the end of it. Note, PB is kind of nice. It's just exactly down to the bottom left. And it's like 2 down and 2 across. So 2 down and 2 across. We're heading to this point. Grab a ruler. Track a little line on. This is PB. And a reminder, if momentum is conserved, then PA plus PB plus PC is going to equal 0, which is to say it's going to be a closed vector loop. So here's how PC is going to look. Right, this is PC. And you can see it's 2 down and 2 to the right. It's going down this way. And again, this is a closed loop. We follow the arrows around, go up, down to the right, down to the left, back up. Hey, it's a closed loop. That means those vectors sum to 0. All of this is to say, where do I draw PC? Like we just saw, the total momentum of PC is 2 down and 2 to the left. That's the vector that represents that momentum. So PC is here. Sorry, 2 down and 2 to the right. So here's PC, 2 down and 2 to the right is this point. So the momentum is down to there. This is PC. And that's us determining the position of the next image. Draw this image. PC is, you know, pretty much a circle. Right? We might label it to be super clear. This is PC. Right? So let's check that we've done 4 marks worth of work. Realizing that P total after or that they're equal to each other. You might say by the law of conservation of momentum. There's basically 1 mark there. There's a mark for realizing that the total afterwards is adding the 3 together. There's a mark for drawing a vector diagram and finding out what PC is. And there's a mark for actually doing what it says and drawing this image. The diagram above. Those are the 4 marks. Hopefully that's clear enough. Again, what we did, found the momentum, the 2 pieces we knew about, realized that those 2 plus PC, which we didn't know yet, was going to have to equal 0, which would mean a closed vector loop, and to do that